Welcome to this first instance of what we call System Talks, and I will shortly tell you a bit more why we introduced this little series. I'm happy to see so many here in the crowd today. We're going to talk English because we have a guest, and our presenter will be English native, or maybe she's Scottish. British. Yeah, that's true. Actually, maybe Scottish people. Right, just to give you a short introduction to who we are here at Syntel. Most of us probably know us already, but anyway, these are the three keywords for our business. It's systems, so we think in terms of the whole, looking at how your system of interest is put into context. We look at the life cycle, so we really like to look at things not just for the operation, but also the maintenance, the recycling, the reuse, and also everything that goes before that in terms of the development and production and logistics and all that. So, and we don't do much CADing or coding. Our focus is on management, helping companies and authorities to increase their capability to manage successful projects and products. So those are the three keywords. So with that, I'd like to announce that this is the first instance. We will have our guest speaker today is Sillitto, and he will be talking about systems, and in particular systems architecting. Here's a bit of data about Hillary, but I thought rather than me talking much about Hillary, I thought maybe somebody could give you a better perspective of who Hillary is and how it is to work with him is my colleague Peter Henriksson, who actually does a whole week every year together with Hillary. So I'd like to hand over to Peter at this point.
Yeah, thank you. I'm sort of the sidekick to Hillary during summer school. I think one of the great things with summer school is that we bring all kinds of people together and with all kinds of backgrounds. And good. Resilient.
It's interactive.
Yeah. No. Bringing people together, and especially with all the field of expertise that people bring into the classroom, it's really an interesting time for us as well, and even a challenge sometimes, with tricky questions and questions of why is it like that, and why do you say that, and Hillary, is that really true? And it's really an interesting week. And maybe the most challenging thing is that most everyone have an opinion about what architecture is and what architecting is. And everyone has read a book, right? So we all know what architecting really is. And I would say, usually start with this one. The only problem is that we've all read different books. That's sort of the challenge here. And in this course, we have the opportunity to use Hillary's book as a textbook for the week. And I like it a lot because it's a very pragmatic approach to architecting. It's no magic. It's sort of demystifying architecture, I would say. And I think that's really, really good. So, in that sense, this whole week is trying to put, you can say, the bits or the good bits of all the books into one book and talk about this for a full week. And we combine both all the core tools you need, talking about views and viewpoints and perspectives. We talk about measures of effectiveness, structure versus behavior, all these basic things, boundaries and interfaces, the biggest problem of them all, layers, granularity, the difference between granularity and levels of abstraction and so on. So this, together with a case study that we try to develop throughout the week, this sort of serves the purpose of both having the theoretical background together with a very pragmatic view of architecting, what it really is, not just a fancy philosophical view of it, but actually hands-on what it actually is. And we also try to get some time to discuss and reflect on this with architecture. What is a good architecture really? And I mean, good is a value statement. So what's good to one person may not necessarily be good to another one. But this is also, throughout the week, we spend some time actually diving into this. So by that, I would like to introduce Hillary. And this will be what the 1 hour version of the
I guess.
60-hour week, or
Yeah.
yeah, please.
Oops.
Yeah.
Sorry.
Let's make
I
sure.
get your, I need to get a little bit of sheet paper. Sheet.
Do we wait?
I don't know.
No, go ahead.
As a professional speaker, you always need to have notes, right? So I'm really happy to have you here, Hillary. You have a long history. So what actually made you become a system engineer or a system architect?
I kind of sort of grew into it, became one, then realised that was what I was called. I started off as a physicist designing optical systems at what used to be Ferranti and is now Leonardo. And I seem to be the person who would keep asking, why are we doing this and how does it fit into the wider picture? So as a result, I got that kind of started being what I did for my job. So I did a lot of work on optics for laser systems back in the 70s and 80s, airborne laser designator pods, complex multispectral optical systems. I think we were taking new technologies and fairly new operational concepts and new packaging ideas to create systems that were pretty innovative at the time. Then we got involved in infrared countermeasures, and I seemed to be the person who could understand how the system was supposed to work and what it needed to be able to do to achieve the operational goal. And I seemed to be able to talk in a language that our American customers could connect with. So I sort of got into this sort of future concepts type of role, and then I moved to what is now Thales in Glasgow, similar domain but mainly land systems, and how could they get more, move up the system value chain as they saw it at the time. I got involved in the systems engineering process approach for Thales, Thomson CSF as it was then. But there was always this, how do we do things that are a bit difficult and a bit different, and we don't really quite understand the requirements and they're probably going to change, and how do we stop just tramlining into a solution that might be the wrong answer? So it was that kind of general challenge, and at some point I read a book by Eberhard Rechten called Systems Architecting, and I realised, oh, this is kind of what I do, and this might help me get better at it. So that's how it all started. And then I got seconded in, well, I got involved in some of the big Thales Prime contracts, the Watchkeeper UAV, the FIST Future Soldier system, some of the big command and information systems we were doing in the early 2000s, and the new British aircraft carrier. At the phase reviews when Thales and BAE Systems were bringing their teams together, and they needed senior people who were, I guess, willing to be naive enough to ask stupid questions, because often the stupid questions nobody dares to ask are the ones that you really need to ask. And then I got seconded into the MOD for 2.5 years running the Integration Authority, which was trying to get oversight of the system and systems integration across the whole of the UK defence capability. And that was very interesting. I wouldn't say it was entirely enjoyable. There was, at that point you realise that all the real architecting problems are to do with people, not to do with technology. The technology is easy, getting people to agree what to do is a much bigger problem. Then I went back to Thales, and for a while I think one of the nicest bits of my career was running the sort of a virtual architects network in one of the divisions in the UK, when we were trying to get the right skills deployed briefly into all the different major projects, effectively using architecture reviews to get new ideas in and to spread learning around the whole division, and also get a better coordination between the British and French parts of the division, because there have been a lot of zero-sum arguments about work share and profit share on joint programmes, which was not helping the overall division's profitability, and it was not helping the customer, so we successfully resolved some of these. And then pretty much the very last thing I did before retiring was helping not sure how much I can say about this, but it's a missile warning project that was doing some very exciting, trying to do some very exciting new stuff. And the project manager said, okay, let's just write the plan, start working now, deliver a working system, then get to it. And there was quite a lot of work to do, and the assumption that the plan was going to work was not a safe one, given the levels of unknown. So it's helping the team to understand what are the levels of unknown here, what are the critical things we need to do to get the algorithms working properly, what are the decisions we have to defer until we're sure we have a workable system. And the last week I was in Tallis, I chaired the critical design review for that job, and then 2 years later it was told they had really, really successful flight trials and sort of unprecedentedly good results. So picking a range of ideas, I mean, I guess the key ideas there were the architecture was developed as a team effort, not by one architect, and using a close approximation to the incremental commitment spiral model, which is do a bit, work out what you've learned, and then decide what to do next, rather than try to run to a deterministic plan from beginning to end with high levels of uncertainty.
I think in this you touched upon it, but can you somehow, in a few words, maybe say why is system architecture important? What's the benefit of having a good system architect?
Yeah, okay, it's if I can define it first in terms of what it isn't, is not jumping to a point solution as soon as you get a problem and have the first idea how to solve it. It's try to establish a framework within which you can do the detailed analyses, the requirements allocation, the work share split. So it's coming up with the fundamental concepts and principles and structures that will make the whole thing hang together. This will relate the solution to the operational problem it's trying to solve, and will then allow people to work in parallel, kind of semi-independently, knowing that everything they do will come together and add up to what you want it to add up to.
So is it some kind of a shared model or
yeah. Yes, I mean it's creating a shared mental model of the problem in the system, and it's kind of deciding what to design before you start designing it, just like the conversation we had a few minutes ago when you came into the room.
Yeah, and as you mentioned design also now, I mean, coming back to our reference works, the ISO standard 15288, system lifecycle and software lifecycle engineering. In the previous version they had architectural design as a process, and now they have architecture definition and then design separated. Why is that? What's the difference between architecting and design work?
Yeah, I mean, the glib way I describe that is architecture works out what to design, and design works out what to build. The other thing about 15288 is that I think the 2008 version said you do the stakeholder analysis and requirements and then you do the architecture and design. What we did, I was involved in the CBOC, the Systems Engineering Body of Knowledge project, starting I think 2010, and there were big discussions about this and the view that actually part of the process of coming to an agreed system boundary and set of requirements, that itself is an architecting process. So the architecture really parallels the requirements definition, system definition, all the way from the initial concept, what is the problem we're trying to solve. So you're applying architectural techniques to understanding the problem space, understanding your system of interest and how it relates to everything else. So if you like, that's architecture looking out from your system before you start thinking of architecture looking into the system, which is the logical or physical architecture of the bit you're responsible for. So I like to think of architecture as paralleling the requirements and other management activities all the way from first question to the solution. And that's reflected in the changes to 15288 to get the business and mission analysis up front along with the stakeholder requirements. So effectively the business and mission analysis is what I would call the operational architecture, and that's reflected in the DoD architecture framework and the NATO architecture framework.
So in a sense you say there's parallelism. I mean, I guess most people already start with a existing product or system architecture. Is that what you see also in reality, or?
It depends. I mean, if you if you are taking an existing product and doing a minor evolution of it, then the requirements the best way to approach that is effectively as a set of deltas, as a set of changes to an established configuration. Most of the systems engineering literature is written in terms of top-down clean sheet, and in reality most of the time that doesn't happen. And when it does happen, you've still got technology constraints coming up from the bottom. I've never used it, but I like the principle of if you're doing an evolution of a design, you do it deliberately, control it as a series of change proposals to an existing baseline rather than as a new clean sheet design, and hope that by magic out of that clean sheet exercise will pop, yes, we can use one of our existing systems. If it's a genuinely unprecedented system, for example, if everyone in the automotive industry is saying how do we get from internal combustion engines to electric vehicles, and the radical thing to do is to say I don't need half a ton of metal sitting under the hood of the vehicle, I don't need 100,000 mechanical piece parts, is it 10 or 100, I'm not sure, in the engine. I just put an electric motor on each wheel and get power to it. So when you're doing that level radical transformation from an existing architecture to a new one, you have a lot of decisions about how much of our legacy, if we get rid of it, do we actually lose all our competitive advantage, versus is our legacy going to stop us doing it right. So I think when you're when you're incrementing all the time, effectively you reverse engineer the architecture that you use, and then you just manage a new product as changes in that architecture. When you're doing a completely new thing, then really you do have to step back and start, not exactly start again, but you've got to divorce your existing solution from where you want to go until you've worked out how to optimize where you want to get to. You then see how much, if anything, you can reuse from what you already have.
So now I think everybody here likes to, okay, now I like to have my system architecture. How would you define it? And then, how would you describe the system architecture?
Yeah, okay, it's the early architecting standards used to say it's a fundamental conception of the system. And I guess nobody really knows how to interpret that. Well, we all do, but we all interpret it differently. So I think they're now homing in on the fundamental structures and design principles. Structure sounds very physical. It might be a logical structure or an information structure as well as a physical structure, but basically everyone talks about architecture. The people who think they're making the running in architecture now talk about it being to do with the structures of the system, whether it's structures of the stakeholder community or structures of the solution system or the data structures associated with it. But the word structure seems to be getting a lot of currency then.
But there's another word also, views, right? That's been used quite a bit. So how does that come into play?
Yeah, well, if you have a complex system, then nobody, the phrase that a British academic 20 years ago came up with is more than one head full. So no one person can get the whole system in their head. And so different stakeholders have got different perspectives on the system, different concerns. So the idea of architectural views is you're describing different aspects of the system from different perspectives. You hope that there's one core system inside there. Quite often when people generate lots of architecture views, they don't fit together. In other words, they're views of the system they'd like to have, not views of one system that everybody's seeing from different directions. So one of the problems of the architecting team is to reconcile all these different views into there is one system in there that can project all these different views to different stakeholders. And it would be nice if we had really good modelling tools that did that, but I guess we're getting there. I don't think we're there yet.
So some of these architecture frameworks put forward, 10, 20, 30, 40 different views. Do you have any favorite views?
I guess one of my favourite views. I used to know all these. I think is it OV2. Effectively it's the operational view that shows all the key system nodes and the exchange need lines are called, but it's the information flows between them. So it's what are the different entities in the operational space and how do they interact. If you don't have that, then really you don't have anything else. If you do have that, then you can deduce an awful lot and have an awful lot of conversations about that. And then when you get within the system design, then the having a coherent logical view of the system and a coherent system view and how they map together become really important. So what's the system supposed to do? How does it work? And what is it? The 40 or 50 views of DODAF, if you try and produce all of them, it's likely to become a box-ticking exercise, and unless you have a very good underlying meta-model, it's very difficult to keep them all consistent. And even if you can, because of the way you have to do quite a lot of bottom-up construction in most current tools in order to get the model to work and hang together, you find, although in principle you're doing it to computers, you can change it, you kind of get there's so much information locked together in these things that it can be, you find that if you build a comprehensive set of views and it all linked together with a single model, you find that it's just about as difficult to change that as a physical thing. So I think it's easy to get into, very easy with these tools and frameworks to get into too much detail too quickly and find that you've kind of locked everything up in this massive detail before you intended to. And I'm guilty of that in the period I was in the MOD. A team I had was doing far too much detail and I didn't understand what was happening in time.
So what would be your advice? How should you approach? Because I mean, I guess they're useful toolbox, but how do you make use of it in the best way?
Well, the thing that I and the guy who took over from me, we worked together for a while in Talis, both found we agreed passionately on was get a team together and get them to mock up the whole architecture and flip charts for a week, flip charts and whiteboards before you let them anybody near a tool. Because essentially you've got to work out the problem and the natural ways of expressing the problem before you start putting it into a tool, because otherwise the tool will tend to map its own perception, that sort of force your architecture into the way its design is assumed. So there's a whole lot of preconceptions and constraints involved, embodied in most of these tools. Of the tools that I've used, and I admit I've not, I used RDD 100 a long time ago and thought it was very good, but it was incredibly difficult to use, and you needed to have a very clear understanding of what you were trying to do and what the tool expected. And I think only about 5% of our people could work out how to do that, as a result of which Talis, having made a big investment into RDD 100, then gave up. And much later they started developing Capella. It used to be called something else, but it's now called Capella. And that certainly works the way I think, but of course I've spent 20 years in the culture that produced that tool, so that's not surprising. Other ones, the trade-off in tools is between, do you effectively build a process into the tool, in which case if the process doesn't match the mental model and expectations of the people using it, then they just get stuck with it. Or do you let people to do anything they like, in which case they will do anything they like, and no two individuals are going to be able to work on different parts of the same model and expect them to come together. So one way of doing this is to say we'll have a team developing, if you like, informal views, and then get a tool expert, put it into the tool, and do an awful lot of reviewing and validating, so that one person can spend his time getting the tool to work, and everyone else can spend the time getting the system to work. And the tool just provides feedback. Yes, the system concept you've come up with actually fits and works together. The idea that you get lots of people doing different bits in an architectural model and then expecting it to come together is challenging. It doesn't work in my experience. And the other thing you don't want is one guy, the geek in the corner, producing a very comprehensive model and not cross-checking it all the time with all the different stakeholders, because then the model becomes a right-only memory. That's not good.
So somehow this fool with the tool is still a fool.
Absolutely.
It's
Yeah.
applicable. Yeah.
You can just make more mistakes faster.
Yeah, a bit more dangerous. So then maybe coming back to, is that the reason why you actually wrote a book?
Yeah.
Or what's behind that?
I spent a lot of time in the latter part of my career working with different architecting teams, and they all seem to have a few basic problems. They didn't have a clear, a consistent way of thinking about logical and physical architecture. They didn't seem to be able to stop and think before either they couldn't stop or think before diving into a tool, or they did everything in PowerPoint and thought they were doing rigorous modelling. And the one is as bad as the other. And there didn't seem to be any book out there that, if you already fully understood logical, physical, and had a quite strong software engineering background, then you could work out how to use the tools. But you couldn't really relate to the other kinds of engineering stakeholders. And if you're an electronics engineer, all you did was draw boxes and wires between them, and you thought you produced a system architecture. And so finding the things that people needed to understand to get from either of those 2 points to able to make effective use of the concepts involved in the tools. So my book's not directed at a specific tool, it's directed at developing an understanding of the concepts that you need to be able to use pretty much any of the modern systems engineering tools. So we start off right with what is a system and what are the things about systems you need to control if you want to produce a good system architecture. And then we go through a sort of 6-step process that roughly maps to the way the architecture frameworks are organised, and by chance, well not exactly by chance, very closely to the way Capella is organised and reasonably well to the way most other tools are organised. But it's all expressed in terms you can deal with on a whiteboard or with Excel spreadsheets. You don't have to use any particular tool to get value from the book.
So, why 6 steps? Is that was that just what?
It just
Because it just
came
fits
out.
that plus minus, plus minus 2. But,
That's an interesting question. I don't know when I came up with 6 steps. It started off looking at the basic structure of the architecture frameworks. We've got in the old days it was called the strategic view, and then it became the capability view, and I called it the enterprise perspective. And then the operational view. Yes, and of course when people in MODAF started talking about operational views, they thought it meant the operational layer of command, and it means nothing to do with that at all. So you've got the enterprise perspective, operational perspective. So the enterprise perspective is really about stakeholders and who cares and what are we trying to do anyway. Operational perspective is how is it going to be used. System perspective is what is it, or how do we split the thing up, split up a system of systems into a series of complementary systems. And that is the level at which you get system specifications and external interface control documents and how we're going to test it. And then logical and physical internal views of the architecture of that system we've just defined. And then decision process. And of course the decision process covers everything all the time. But separating that out, a lot of people forget that the architect or the architecting team are the people making the key decisions about the system. And so there's a bit of stuff about decisions. So that is the 6 steps. Having gone through one spiral, what are the decisions we have to make in the next spiral, if you like?
In terms of applicability, I mean, of course you come from sort of the defense background, but what other businesses, industries, social problem, where do you see this applicable and where is it going right now?
On Friday I was talking to people in the UK who are trying to integrate the energy and transport and ICT sectors. And the workshop template I put together for them was basically the first step of my book, and it might be that we'll end up using that in the next version of the course. So and we're seeing systems engineering increasingly used in healthcare, in energy, in transport, lots and lots of civil sectors. There's a belief among a lot of people in Nkosi that you can systems engineering or a systems engineering approach or a approach drawing on good things that systems engineers do are relevant to social and social technical systems as well as to technology-based systems. And of course there's already an established domain of enterprise architecting, which you can argue is coming away from the technical layer and looking at the whole enterprise. Some people in the socio-technical world get very upset when they see the word engineering. And I don't know how it is here, but in Britain we have these two cultures, sort of evidence-based engineering and science and emotion-based arts and politicians. And I'd better stop here or I'll put something on video that will get me not allowed back into my country. But if it's presented as systems engineering, then that engineering is a trigger to some people. So I don't know, I've actually got a paper, I and a group of INCOSE fellows are trying to wrap up some work about where should INCOSE be trying to position systems engineering for the future. And we put together a paper on envisaging systems engineering as a transdiscipline, which is very much saying, abstract away a bit from the systems engineering process you get in the INCOSE SE and how widely are they applicable. And there's quite a Bristol University, for example, are doing a lot of work on they're branding it as systems thinking rather than systems engineering. Thinking is all right for non-engineers, engineering possibly isn't. On the other hand, if you talk to some systems thinkers, say the systems are imaginary, they're not real, there's no such thing as a real system, which personally I don't agree with. So there's about 7 different worldviews on what a system is, just within the 50 or 60 INCOSE fellows. There's more consensus on what systems engineering is, but there's still a spectrum, and I'm getting vitriolic abuse from both ends of that spectrum at the moment as we try to tie everything together. So what was the question? Did I answer the question?
Well, I mean, yeah, where is systems engineering or system architecting, architecting applicable?
I guess the big transition, and this is what we're talking about in the KTH workshop tomorrow, is from defining systems that are essentially, in some sense, deterministic. You guarantee a given output for a given input, which means you have to define a constrained set of environmental inputs, to systems that will do something sensible in a non-deterministic environment. What does that mean? And that's kind of this decade's question, I think, for systems engineering. Is there such a thing as a dependable system? Can you define such a thing as a dependable system in a non-deterministic environment? The challenge going from precisely controlled systems to some extent autonomous systems.
So, considering the environment we live in now, and lots of systems are dynamic and they sort of are connected in ways that were not intended to. Where do you see systems architecting going in that context? Why?
It's probably got to do 2 different things. It's got to map out the range of possibilities. What is the problem? How does it manifest itself? And then really make the decisions about which bits of the system should be pinned down and which should be allowed to be flexible. The internet's a good example. If you follow the TCP/IP protocol, you can connect any internet-connected device to any other one anywhere in the world, and you can do anything you like based on, provided it's legal, or even if it's not legal, there's a whole lot of different business models you can build on top of that without needing to change the core system. So it may be that systems architecture needs to change from controlling everything to defining that which has to be controlled and that which has to be left to future innovation.
Some years back I saw a paper, I think from MIT, where they talked about hot and cold spots in architecture. Maybe that's one way of looking at it. That's
possibly. I guess you could say one of the key architecting decisions is what you're not going to try to control with the architecture.
Right. You mentioned a tool. I mean, you're not used the tool at all that you have at disposal. Any pictures you like to create, or do you want to just maybe give us some of your key insights to architecture verbally?
Key insights to architecture. We've got a few slides that we can run through, but I guess key points is people. It all sounds a bit negative, but what you're trying to prevent is jumping to a point solution before you've properly understood the problem and properly considered the alternatives. And locked into a kind of complete design that you then find is very expensive to change if you get a new requirement. I don't know how many of you are in government, how many of you are in industry, but if you're in industry, you've had the experience of you've spent the last 6 weeks working in a bid, you've got it just about all together, you've costed it, the cost comes out as too high, you then have to take 30% of the cost out to get to the target price. And you can't find any way of taking 30% of the cost out without throwing everything away and starting again. So one of the things about architecture, I think, and this is something that's easy to say and really difficult to do, is understand what's likely to change and try to maintain, you need to do this in project plans as well. The plan and the architecture need to have flexibility to match the level of uncertainty and the likelihood of change. So one way to deal with, I know I'm going to get hit with a 30% cost reduction, nobody's going to admit it yet, actually run 2 solutions in parallel, which Toyota allegedly do, and it's called set-based concurrent engineering, and that actually works quite well. We were not allowed to do it in the aircraft carrier, and that's why the aircraft carrier came out so expensive.
So, but they didn't follow your 6 steps then, I suppose.
Well, if on the carrier, well, when you have political intervention, no, you must not admit to the possibility of trading requirements. You must not admit to the possibility of the referendum coming out the wrong way. There is a macho political culture in some organisations that makes it really difficult to do the right thing. And then you either just do what you're told and say, I told you so, and it goes wrong, or you run Plan B in secret, depending on how much authority and flexibility and independence you've got.
Yeah. Talking about slides you want to share with us at the point
you
have
got it.
Yeah, you got it.
Yeah. So that comes down to this. I think is my favourite statement out of Recton's book. Don't assume the original statement of the problem is necessarily the best or even the right one. So that comes straight down to applying a bit of architectural nous to does this problem statement make sense is where you should start the architecting. Don't wait until somebody's got the wrong problem statement of 1,000 requirements. So why does it matter? More software, more connectivity, more socio-technical complexity, shorter time to market, please make sure nobody sues us. That's an interesting one that people are getting very hung up about at the moment in autonomous vehicles. And it looks as if one of the solutions is that if autonomous vehicles are owned by a fleet, then you spread the risk enough that somebody who designs them can probably underwrite the insurance of them. If I buy an autonomous vehicle and expect it to take full legal responsibility for software going wrong in a system I don't understand and have no control over, that's a problem. So better architecting, we claim, is a partial solution to these challenges. It's not a magic bullet, but this is saying that's the Meaux suspension bridge in France, which is beautiful. It's interesting, actually. Apparently, the British proper architect, not systems architect, Norman Foster, apparently has something to do with this. You do not see his name mentioned anywhere in the visitor centre. There is some French guy who did the sums to make sure it would work, and he is given due recognition, which I liked, because if somebody actually sat down and did the sums and said this is going to work, that's a much more important contribution to the guy who said do it this and it will look pretty. That they've managed to do both is quite an achievement. So fitting together, working together, creating value are 3 different problems. Somebody said to me, if it fits together, then surely it will work together. To which the answer is not based on the experience of many, many bits of my boat that fit them together and nothing happens. Fit them together, fit them on, they do the wrong thing. So there's a difference between working together and fitting together. and then again creating value. So we're kind of saying fit together and work together, if you like, are hard engineering. Value is a societal judgment, not an engineering judgment. So architecture is actually the boundary between engineering and societal value and perception. And in terms of an engineering project, you get the architecture right and you have got coherence and a shared vision. That means when you've got 1,000 people working in 20 different teams, what those 20 different teams do will come together in the end and work, come together, fit together, work together and create value. So this is the 6 steps, we mentioned them already. And 3 real viewpoints: looking out from the system, looking at the system, what is the system, and then looking inside it. So the enterprise perspective, and this is, social, who cares, engage the stakeholders, what are their different expectations, requirements, how much leverage they have, are they funding the system, can they veto the system. Typically we do this bit in terms of a very sort of soft systems process, the Checkland lit picture kind of analysis. That's really good for getting people's views and attitudes and concerns out, but you end up with lots of fuzzy pictures that people spend ages and ages and ages refining, and then you have to do something with that. What you have to do with that is actually turn it into some sort of organised structure. And there's a lot of stuff that John Warfield wrote about back in the 90s about what he calls interpretive structural modelling, which is basically finding which of these things interact with each other, which of them are independent, you can do that and that and that, just spend money, you'll get the answer. Which of these issues are mutually reinforcing, everybody wants the same thing, so have a basis for a common approach. And which of these things are apparently in conflict. So electric vehicles, for example, I want to switch the entire diesel and petrol fueled fleet to to zero carbon over the next 30 years. It's either electric or hydrogen based. I want to reduce national level carbon emissions, so I want to decommission all my coal and gas fired power stations. And wait a minute, everybody's going to be, at the moment in Britain we heat our houses using mostly burning gas. So we're going to replace gas central heating with heat pumps, and we're going to replace petrol cars with electric cars. And it turns out at the moment our electricity grid generates about, the average consumption is about 45 gigawatts. It's going to go up to 70 or 80 if you just have to charge all these electric vehicles and drive all these heat pumps. So what are we going to do? Let's build lots more gas-fired power stations. But we did all this. Or let's build some more nuclear power stations. But at the moment, the world seems to be in an interregnum that nuclear has lost the plot and they haven't yet. So you see these trade-offs. So what we're doing Friday actually is starting to map out what are the critical interactions, and the most critical interaction of all was if you're going to need an extra 50% generating capacity, what are you going to do about it, given that you're decommissioning power stations faster than you're building them at the moment. And of course there's a hidden trend here, because until 2030 people are going to be buying diesel and petrol vehicles, and people who want to have diesel and electric vehicles forever, are going to wait until December 2029. There'll be a huge lot of them sold then, and then suddenly there'll be a huge ramp up of electric vehicles, and the grid is going to have to find a way of dealing with this. So structuring the information lets you see these things that are probably going to happen, that you don't necessarily get out of this, because the rich picture is a static view. You need to turn that into 2 other things: a set of interrelationships between issues to find these sort of pressure points, and time sequences that tell you what the critical timings are going to be. Agreement and common purpose, so Get a Man to the Moon is about the best purpose statement ever. We use that in the course. Map out the full context to understand how you fit into stuff around you. On Friday we took an apparently very simple use case for an electric vehicle, and found that by spending half an hour analysing that use case, we could map out a very large part of 3 systems of systems, including bits that none of the people in the room realised were relevant to that use case. So the business of actually getting very specific and doing a little bit of analysis and forcing yourself to think through the implications generates far more information than you think. And then measures of effectiveness. So what are the things that matter for different stakeholders, and are they in conflict, are they in synergy? Operational perspective is what are the missions, what are the scenarios, what are the use cases. We can have lots of fun talking about what we mean by use case, what we mean by mission thread, what we mean by a scenario. I don't want to go there. Alternative operational concepts. These pictures have lost a lot in the telling, but if you want to make a journey, do you go by plane, do you go by train, do you go by car, do you cycle, do you do video conferencing instead? So the business of actually tracking mission threads end-to-end value. So it's not, if you're looking at transport, it's not I arrive at the airport, I check my bags in, I go to the baggage terminal at the other end, I pick up my bag and go. It's, I'm sitting at home thinking about this journey. What's the information layer? How do I synchronize things? Do I get a taxi to the airport? If there's 1,000 taxis going to the airport down a one-lane road at 6 in the morning, what happens? My son works at Edinburgh Airport. He tells me that there's a traffic jam every day on the way into Edinburgh Airport at 6 o'clock in the morning. These things are real. So the end-to-end aspect of a mission thread is what's valuable, and that you understand all the pinch points all the way through the wider operational architecture. And then you try to tie that together into a sort of ConOps or day in the life of the system. And establish, from measures of effectiveness to measures of performance. So where are the critical pinch points? What are the things we can do to the system to make it work better? And then the system perspective is, okay, what is the bit I'm responsible for? What does it do in terms of function performance? What are its interfaces? And what are all the other things that we didn't pick up in the operational analysis, interface design, dependency, resilience, through life cycle constraints, can we test it? Can we validate it? How do you do test or validation for ballistic missile systems? Slightly tricky. And then logical perspective, I describe this as a glass box view of how it works. So if you like, system is a network of processes with flows of material, energy, information through processes. And then identify an existence theorem. There's at least one class of generic component that can actually do this. One of the biggest issues, I think, for most systems engineers in this logical or functional decomposition is saying how far do you take the decomposition? Because when everybody was following the Urdan methodology back in the 90s, that told you to go all the way down to pseudocode, which effectively said down to detail, almost formal specification for the software. In systems engineering, you're not trying to do that. You're simply trying to get to the point you can allocate requirements to subsystems or bits of the system. So the trick here is how little do you need to decompose rather than how much, because if you do too much decomposition, then you're accepting all the responsibility for the consequence of all the decomposition decisions. If you're engaging a subcontractor to do that bit of the work, you want them to accept the responsibility. Otherwise, when it doesn't work, they come back with a bill to you for doing it again. So, so the key point is when you identify generic components at this level, you're not saying the design consists of these bits. You're simply saying there's at least one way of doing it, and then you rub that out. Allocate performance. So the important thing about the logical architecture, and this comes back to the point of you have to change the design to reduce cost. If I only thought of the design in terms of physical components, I lose all the function and performance information as soon as I throw components away. If you have a logical view of the system with function and performance allocation, then if you decide that bit is too expensive, you can substitute a cheaper bit or a cheaper organization and retain the logical architecture and the performance information and have a much better idea of what's going to happen. And if you want to do technology substitution, if you're designing generation 1 and then you're going to replace it with generation 2 or 3, if you've got a good logical architecture, it's relatively easy to specify the replacement part, see what happens if you group 2 or 3 subsystems together, or whatever. If you don't have that logical bit, then you effectively have to reverse engineer it anytime you want to do any change to the physical architecture. And system-wide design decisions, That's, that's not a very good illustration of a logical view, but things like the TCP/IP or consistent layering principles you want everybody to use. And then the physical perspective is, oddly enough, this is kind of the most difficult. This is where people run out of steam. Actually, it's where we run out of steam in our course, because this is usually Thursday afternoon, and you need a lot of domain knowledge to get a good physical architecture. But also, it's something a lot of the textbooks don't make a very good job of explaining the difference. So we tried quite hard in my book, and we've been working very hard in the course over the last few years to get a better way of explaining all this. And I think we're succeeding. But so what's it made of? And then a lot of standard product design engineering stuff comes in at this point. What are the alternative component solutions? Are there sets of solution elements that work together to give you good, if you like, modular partial subsystems, partial systems? That's represents a Q matrix to choose between alternative concepts. And then once you've got a feasible and affordable solution, what is the modular organisation you want? What's the commercial organisation you want? Try to get the physical and functional and commercial and project organisations all lined up to each other, so that you don't generate, having reduced complexity by coming up with a good technical organisation, you don't want to increase complexity again by mapping a completely different commercial organisation on top of it. And decisions, I think of the whole architecting process as a kind of multi-spiral approach, process, life cycle, call it what you like. And at each stage you've got a series of decisions to make. And one of the important things to do is understanding which decisions are related to each other, and which decisions drive other decisions, which you can't make until I've made other ones, which decisions reduce the trade space for everything else. So one of the important points about decisions is that you need to make the most difficult ones first. And so if the difficult thing is a technical challenge like getting to the moon or getting to Mars, until you've worked out how you're going to get 3 men to the moon and back again, you shouldn't be deciding what material you're making the rocket booster out of, or which company is going to make a bit of the system we haven't yet defined. If, on the other hand, the most difficult problem is getting the stakeholders to agree on anything, then maybe you produce a cheap technical system, let them play with it and see what happens. But the general principle is that each decision reduces the trade space for all the downstream decisions, and the most difficult decisions are the ones you need the most trade space to play with in order to be able to get good solutions. So understanding the decision sequencing, understanding what you don't know and what's going to change. So there's this concept of the Italian flag. Stuff that we know is green, stuff that we know is bad, stuff we know is good is green, stuff we know is bad is red, stuff we don't know anything about is white. And that missile warning project I mentioned before, they've been doing red, amber, green risk stuff, and every time they tried to discharge a risk it came back again. When we did an Italian flag analysis, what do we know about this, what don't we know? It turned out that most of it was still white. They've been worrying the problems that we knew about, and they've been ignoring the problems that we hadn't yet identified were problems. And that changed the perspective, and it allowed us, by concentrating on get an answer to that question. I don't care if it's red or green, but I want to know how much of that white is going to go red. We made progress. It started working. So up and down the staircase several times. Whoops. And I guess you know you've got somewhere when you can firmly define the system boundary, and you can make some interface decisions. So the process will only start converging when you've generated enough information to define boundaries and make key interface decisions. And then you can move on. Until you've got to that point, you need to keep cycling. That is a summary, which I won't bore you with trying to read out, but we've managed to get the course on one page. And a few of my favourite heuristics. Einstein, of course, make things as simple as possible, but no simpler. We mentioned that one. Design is what to build, architecture is what to design. Rechten points out that no complex system can be optimal to all parties involved. And Bud Lawson, our local hero, we'd say that the secret of the good architecture is a small set of driving concepts and principles. And I think that's it. Well, that's the course that Peter and I are running with Tom's help in August in the beautiful island of Utah. And if anybody wants to have a discussion, you might want to consider these points.
Yeah, thank you, Hillary. And talking about the course, how do you manage to get people through this? You mentioned the case study.
Yeah. Well, one of the things that I worked out about systems architecting is it doesn't matter how much you try to explain it to people, they don't get it until they try it. So we have been, a key part of the course is a case study, and we've gone through a number of different iterations in the case study. Last year we got it nearly right. We gave 3 different, I think we started off with quite an open, unbounded case study, and the result pretty much was chaos. And basically it was a matter of if people could hold on to anything, we allowed them to carry on with that. The second year, I think we tried to get everyone doing the same, and the problem with everyone doing the same one is that by the time the 3rd or 4th teams presented their solution, it gets a bit boring. Last year we had, I think we had 5 different case studies, and each team, there were 3 teams, so we had 3 different ones running. The one of them that worked the best, we realised that what we're doing this year, we're framing that as a systems problem, with some of the enterprise level stuff already done, and we're going to take everybody through the mission thread analysis, and then we're going to segment the system 3 or 4 ways, and ask different teams to work on different subsets of the system. Big value of that is the behaviour that you see every time in these exercises is people throw scope over the wall. Because simplify the problem so to something we can solve. If you have to negotiate rather than just throw, then it focuses your mind on getting the system to work rather than simply fulfilling the contract. So we think this is going to work really well. We spend most of the day working through how we're going to do this. So, and previously we'd introduced the case study after the first full day. This time we're going to introduce it here so that people can be thinking about it from while they're drinking their beer the first evening. And the other thing is we started off with the idea of design review at the end. Design review triggers everybody into adversarial behaviour. Whereas the scenario we're now going for is a collaborative architecture workshop. You're the core team that has developed the first stage of the system concept. You're now bringing the rest of the team on board. You're describing it so that they can get up to speed. They're critiquing it and trying to improve it. So it's all about getting architecting thought of as a team activity rather than an individual one. And all the case study stuff and the collaborative workshop are the highest scores in the course feedback. It's quite noticeable.
Yeah, oh, it's going to be interesting to see if you can break the score from last year because it was really good. Okay, so I think I'd like to open up the floor, so as it's called. Use some ideas, some questions, maybe that's, or some reflections. Robert?
I have a question. Yeah, Robert Nilsson, I work for Volvo Car Corporation. Looking into the systems engineering as a community, people like in codes, where would you say that the communities and the maturity and when it comes to the system architecture versus system design? Have we as a community understood the difference, and do we have the capability of practicing that, or are we still learning ourselves?
That's a very good question, which I'm not sure how to answer. First of all, the community of INCOSI is quite diverse. I'm just thinking, I mean, there's the new standards work that people are doing on which Johan's involved with, on what are the standards for systems architecting. One glib answer is I would not have needed to write my book if there had been a clear answer on that.
No.
So by definition we're still learning. Are we getting better? I think we are, because there's a few books came out soon after I published mine that if I had known they were coming out, I might have thought I can spend something else. I can spend my year a different way. Not entirely, but I think if you look at what's been coming out over the last few years, I think we're doing that. I'm not sure where there is, but we're definitely doing that. There's definitely, you can have conversations now that you couldn't have 10 years ago, and you can close conversations more quickly than you could 10 years ago. So I think definitely there. There's still a gap between people to whom the tablets of stone cast down by ISO and INCOSE SE. The latest INCOSE SE handbook is a big improvement in the previous ones. But there are people who say, we've done it now, that's the tablets of stone, do that. And others are saying, have you not noticed what's happening? The definition of systems engineering says, write down your requirements at the start of the job. Well, in a complex system, you don't know what your requirements are until you've got a system working in the field and you see what really happens. Which says you need to get some baseline that lets you get something out there that will let you learn. Yes, I think the idea that a systems engineering project is a learning journey. It's not just a deterministic delivery of a product against requirements of the baseline at the beginning of the project. The team of fellows I'm working with gets that, but we wouldn't have to do the work if it was other people didn't.
Yeah. More questions, reflections?
Can I get some, is that water in these cans?
Go ahead.
You want the main here?
Yeah, I have we have a big discussion in FMV around the benefit of systems thinking. And I'd like to hear your 5 cents or pence or whatever on what really can be sort of seen as the added value or the contribution that SOS thinking does to what systems thinking did before. Some of us are sort of only slightly optimistic because we come from a sort of theoretical systems thinking world where we have agreed that all systems are parts of higher order systems and they consist of lower order systems. So nothing is new, right? Every system is also a system of systems. So what's particular with this new category, this new realization that is sort of emerging?
Well, having been, I guess, closer to that world 10 years ago than I am now, the thing that differentiates a system of systems, the two things are operational independence and managerial independence.
Mm-hmm.
And those are attributes of the organisation around it, not the system itself.
Uh-huh.
So any system of systems that is doing anything is configured as a system for the period it's doing something.
Yeah.
And then it goes back to being something different. So the real system of systems issues are managerial and not technical. They're how much control over your system are you willing to give up in order to achieve the purpose of the system at level above. To be honest, I haven't even looked at the last couple of years worth of outputs of the INCOSE Systems Working Group, so I'm not quite sure what they're saying. And the other thing is virtually every real system that we're dealing with in current practice is a contributor to, operationally it's a contributor to one system at level above, commercially it's a contributor to another system at level above, whatever. So I'm afraid the answer is I'm so far out of touch with what people would now call systems thinking, I'm not very sure. But I think to me that all gets subsumed in the transition from the view of systems as pseudo-deterministic to the view of systems as complex.
Yeah.
And it might be that system of systems are just a convenient mental hook to get us there.
There is informative stuff in the current 15288, right, at the very back, which sort of talks a little bit about a possible taxonomy for SOSs, and then there are people in the ISO room who've sort of gone off to the corner and started writing possible standards on SOS, and they deem them, they have a standalone value set apart from the standards on systems. And so I'm just sort of watching this process with interest.
You know, the last serious thinking I did about this was to work out that you have typically you have systems use cases that you want to have available. Effectively, it's in the if you're designing a system and it needs to be part of the system of systems, then ideally you provide affordances for system use cases. But the question is, do I provide them generically, or is there some authority that's going to say, I want you to do this now? So what exactly do you mean? I haven't found it necessary I haven't found it necessary in the last 5 or 6 years to consciously differentiate between them. If anything, I find it more necessary to say it's only the managerial aspects that are different. Okay, system of systems is you've got dynamic reconfiguration, so it's a complex system in that sense. You've got the resource contention between doing the local job and doing the global job. And one model is I'm pulling a lot of available assets together temporarily to do a particular mission thread, such as an air sea rescue. And the other is it's continuous steady state systems like air traffic control worldwide. And is it a one-off or is it steady state is maybe more important than is it a system of systems or is it a system. So I think it's purely a management distinction, that you've got different allocation of responsibilities. I don't think technically there's any fundamental difference. Or all systems are now becoming systems of systems because you use different words at different times. I don't know. Has that helped, or has it really confirmed that you're right to be sceptical?
No, but
if I can comment, I find it most similar. I think it's managerial, but it's quite powerful when it comes to discussions like business cases and sharing of responsibility. But that's managerial aspects of the technical reality. I want to. Okay.
Yeah, I guess. Yeah, when you're thinking about a lot of the infrastructure discussions in the UK at the moment, the issue is you've got your project and your budget. Everybody can see that you're part of a system of systems, but nobody has got a way of funding you to provide the affordances needed for the system of systems thing to work properly. And the term I'm using at the moment is you have an enterprise ecosystem embracing several of these things, and you need to lift your thinking to that level. But yeah.
That's one of the definitions of enterprise, isn't it? Sort of interested parties coming together for a period of time to achieve something together and then dissolve. So it's very akin to the notion of enterprise in itself. No. Oh. Okay.
Yeah, we had. I remember we had discussions in one project around systems, and it may start as a system of systems because you're still. You were not meant to work together as a system, but eventually, that system becomes a system, as you get things organized around it. And so so that's another way of looking at it. But maybe these days you need to be dynamic. Sometimes you have a complete system, then you take parts of it and put it into another context, and maybe that's where architecture comes handy.
Yeah, I mean, one of the things that. Yeah, about 10-15 years ago, the UK was buying strategic, operational and tactical communication systems. And I think it was Falcon was the operational level one. I can't remember what the partitioning was. But it was designed and contracted and delivered against a particular use case. And then when we were on actual operations in Afghanistan, we wanted a different use case, and basically we wanted to use Falcon as a Lego kit to connect other bits of the system in a way that had not been previously considered. And there was all sorts of arguments about that's out of scope contractually, and we never designed it to do that, and isn't going to work. And people fixed the problem. But that, an example, so that again is a procurement issue. If you want to buy a set of Lego blocks or IKEA modules with a deliberate intention you can configure them in different ways, interact in different systems, the best way to get hold of it actually is to work out the test cases in terms of different system mission frames you want to be able to do. And then potentially you can certify the parts as they worked when they were connected to these other parts in that set of use cases. So if it doesn't lead to a concrete decision about some specification or text or something else, then maybe it doesn't matter, or maybe it's not helpful. If it does lead to a concrete decision, then it is helpful.
Any more questions? Yeah.
Yes, I have one more question. Do you find this more difficult to talk about, the architecture of systems architecture, than the system design?
In a way, I think it's easier because system design is meaningless out of context. You know, I could talk for hours about designing how lens systems were designed 30 years ago. System design, you kind of need to be within the context of a particular domain or a particular discipline to have a sensible conversation about it, I think. I can't talk terribly sensibly about designing electric motors for electric vehicles because I don't know what the fundamental constraints and trade-offs are. As a system architect, I can probably work out fairly quickly what the right questions to ask to get you talking to me about it. So I think how to design a particular kind of system in a particular domain depends very, very much on how the technology is evolving, how the technology constraints interact with the domain constraints. Systems architecting is really, I guess, really fundamentally about putting different technologies together, different domains together, or maybe even different generations of technology within a single view. So you can maybe, as a systems architect, you can have more conversation, you can learn more, you can have conversations as a learning process about a new discipline. Whereas if you're trying to do system design, that depends on being steeped in that discipline for a long time, because there's a lot of tacit knowledge in design about the things that matter in order to do things. A very interesting question. I've never thought of that way before.
Thank you.
Because as soon as I start talking about anything with design, I want you to understand all the domain knowledge and experience and background and technology history and nature of glass and nature of metal and things like that.
So,
anyone else?
Anybody else?
Now, if this were the summer school now, we'd go around each individual and say, what do you want to say?
Yeah, well, you have the opportunity, of course, to be exposed to that later on in August. With that, I think I'd like to thank you, Hillary, for this, and of course, we hope to see some of you maybe at the summer school where you can then judge whether Hillary and Peter has architected the course correctly. And of course, the design and the implementation is very much up to the participants. So, but it's normally a very useful experience and lots of fun in a good environment. Lots of hard work, actually. So don't take it for granted. But talking about lots of hard work, it's been a long day. We have, I think, we have some supplies in the back here. But we would also like then, of course, to see you back here. This was the first instance of this system talks, and we're going to do this on a regular basis from now on. And we have some, if you have suggestions who you would like to have here, I know we have probably one of the other fellows in COSU profiles, James Martin, coming up in May. So probably going to talk about system thinking then. So with that, we'll keep you posted, and thank you for being here. And of course, now with some good some food and some more drinks, maybe you want to share additional questions or ideas.
Good.
So with that, thank you for today and
Thank you.
have a good evening.